Oh, we seem to be running out of chalk. Yeah. Is this, what is, do I have to do anything?
No, this is.
Okay.
This is for them to sign.
Okay. Okay, so let's see, we were talking about, oh, thanks, Ying-Ing, thank you.
Maybe just start.
Yeah. Grab a couple more pieces while I'm at it. So we were talking about Lipschitz functions, and the first theorem concerning Lipschitz functions is this one that that if you've got a Lipschitz function from a set A into the reals, and A is contained in a metric space, then, and this is Lipschitz. So in particular that means fx minus fy, absolute value, is less than or equal to L times the distance in the metric space from x to y. And the theorem there was that there exists an extension. There exists an f bar defined on the whole metric space with the same Lipschitz constant times the metric distance, and that would be then for, this would be for every xy in the original set, and this one would be for every xy in the whole space. So it's an extension, and it is really an extension. That is, f bar restricted to A is equal to the original function. And you remember we started the proof of that. The proof is pretty easy. We started the proof by simply defining f bar. So define f bar x equals the infimum over y in A. I guess I should be a bit more careful. This is a non-empty subset. Otherwise, it doesn't make much sense. And you take the infimum, and then you take fy plus L times the distance from x to y. And we checked, just by using the triangle inequality, we checked that f bar is indeed bigger than minus infinity for every x in x. So that means that actually f bar really is a map from all of the space x into the reals. It doesn't take the value minus infinity. So it's a real valued function. That's the first step. And then we want to check that it's Lipschitz. We want to check this property. Okay, so let's take 2 points, x1, x2, in the space. And let's check. F bar x1 minus f bar x2 is equal to the infimum of this, so it's inf over y in A of fy plus L times dx1y, and then minus the inf over, say, z. Just, it's convenient to use a different letter here, so let's call it z. Z in A of fz plus L times dx2 z, distance. L times the distance from x2 to z. So that's the definition. Now the trick is to notice that you can write this as the sup over z of the inf over y of, then you take the difference of these two, fy minus fx, minus fz rather, plus L times dx1y minus dx2y, 2x dx2z, like that. And yeah. See, that's correct, isn't it? Because the minus the inf is the same as the sup of minus, right? So it's the same thing, just a change of notation. But then that's good because the inf is always less than or equal to any value of y that you like to put in here, right? So you can take, for instance, y equals z to get those two to cancel out. So this is then less than or equal to the sup over z in A of, and these two cancel out as I said, and now we've got y equals z. So this is L times dx1z minus dx2z. A sup of that. But now we can use the triangle inequality. One of the versions of the triangle inequality says that this is less than or equal to dx1 x2. So that's it. So f bar x1 minus f bar x2 is less than or equal to L times dx1 x2. So that's great. That's f bar really is a Lipschitz function. What's that? Yeah, okay. So, right, I should have said that. Yeah, thanks. This is only half what we want to prove the absolute value. But of course, there's nothing to prove because you can just flip x1 and x2. So this is enough. Since it's true for every xy, it's enough. So that is the Lipschitzness. And the only thing left to prove is that f bar does agree with f on A. Notice that's not quite obvious from the definition, actually. So we need to check that. So let's check that f bar x does indeed. So take x in the set. And let's look at f bar x in that particular case, right? Well, if x is in the set, then we can take a y equals x in this definition at the top of the board there. And that means and then the second term cancels out because dxx is 0 in that case. So you simply get that f bar x is less than or equal to fx, trivially. So that's no problem. But now we want to prove the reverse inequality. So let's try that. F bar x is equal to this inf fy plus L times dxy. And now here's the trick in this case. You simply add and subtract the fixed term fx here. So this can be rewritten as fx plus the inf over y in A of fy minus fx plus L times dxy. And then this guy is bigger than or equal to minus L times the distance from x to y, because that's the Lipschitz condition. Without the absolute value, you get that inequality in particular. So that these cancel out, so that's bigger than or equal to 0. So this is bigger than or equal to f of x. There we are. So you get both inequalities, and indeed this is true. On the original set A. So that's a nice extension theorem, and we'll make use of it from time to time as we go along. Okay, now we want to prove something much more important and much less obvious. That is the famous Rademacher theorem. Rademacher's theorem. And that simply says that if you take f from Rn to R Lipschitz, then f is classically differentiable almost everywhere. Lebesgue almost everywhere implies f is differentiable. Ln almost everywhere in Rn. Now let me remind you what that means, of course. We're talking about functions of n variables here, so what does differentiability mean? Well, it means the same as it does in one variable. It means that if you take limit, what has to be true is that limit as y tends to x of the absolute value y minus x to the minus 1 of fy minus fx minus minus v sub x y minus x equals 0. So actually, let me, that looks a bit abstract, so let me say it in a slightly more concrete way. Because it's silly to state it in such an abstract way. So I claim that f Lipschitz implies that all the partial derivatives exist at least almost everywhere. So you take the partial derivative. So dj, just as usual, means the partial derivative with respect to xj of f at x. That means the limit as h tends to 0 of fx plus hej minus fx over h. That should exist. So the claim is that they exist ln almost every x in Rn. And f is differentiable. Ln almost everywhere. That is, let me remind you that that means the limit as y tends to x of the the distance y minus x to the minus 1 times the absolute value fy minus fx minus the dot product y minus x dotted with the gradient of fx. Gradient of fx just means that should be 0, and of course, as usual, gradient of fx means the vector of these partial derivatives. So that's the Rademacher theorem. It's a bit surprising, actually. It's, I mean, if you play around with this Lipschitz condition, it just says that the function's got bounded slope. Even in one variable, you can make an awful lot of wiggles without making the slope unbounded. As long as you keep the slope bounded, you can have as many of these corners and so on as you like. And a little bit surprising that this classic, notice this is classical limit. So it says literally that if you look at the graph of f, which might have some corners, right, because it's only a Lipschitz function, this would be the graph of f. That's the set of x fx such that x is in Rn. And the graph of it, this says exactly that the graph of x has a tangent plane, a classical tangent plane almost everywhere. Really a bit surprising at first sight. And of course, needless to say, it does require a little bit of proof. So let's check the proof. So first thing is, let's talk about directional derivatives. The proof is actually based on using directional derivatives. This proof, by the way, is due to C.B. Mori, famous American mathematician from the, he died only around 15 years or so ago. He was a professor in UC Berkeley, famous for his work on partial differential equations. Okay, so first of all, we want to talk about directional derivatives. So take any point of any vector, first of all, in the unit sphere. This is the unit sphere in Rn, set of points in Rn with norm equal to 1. And then we define d sub v f at x to be the directional derivative. That's the limit as h tends to 0 of fx plus hv minus fx over h. And we do this whenever this exists. Notice there's no guarantee this exists everywhere, of course. It's only a Lipschitz function. But whenever this exists, we make this definition. So whenever this exists. Notice there's another way to say this. It's exactly equivalent to saying that the total derivative ddT of fx plus tv evaluated at t equal to 0 is equal. This is exactly the same as the derivative with respect to the t variable. It's exactly the same thing. So so we do that first, just to set up notation, and we're going to talk about the fact that these directional derivatives exist almost everywhere. That's the first step in the proof of this differentiability result. So let's do that first. Well, the first step is to take v equals En. So v equals En, which is the nth basis vector. That's the one with coordinates, all zeros except for the last coordinate, which is 1. And let's simply, so then den in that case, dv fx in that case is just the nth partial derivative. By definition, that's the definition of the nth partial derivative of f. So this is dnf at x. Of course, whenever that exists. We don't know yet where that's true, whenever this exists. Okay, so we do that first of all. And now keep in mind that these quotients are all bounded by the number L, because it's a Lipschitz function with Lipschitz constant L. So fx plus, or generally fy minus fx, a ratio like that is always less than or equal to L for every y not equal to x, because it's a Lipschitz function with Lipschitz constant L. So that means that these, even if these don't exist, the lim sup and the lim inf have to still take finite values. They can't take values plus or minus infinity. So let's look at the lim inf and the lim sup. So, so dnfx exists is exactly equivalent to saying that the lim sup as h tends to 0, yep, of fx plus hen minus fx over h is the same as the lim inf. Because remember, limit exists if and only as long as everything's finite. The limit exists if and only if lim inf equals lim sup, right? So lim inf h tends to 0 fx plus hen minus fx over h. And let's consider the set of points E. Let's let E be the set of x such that these are different. So set of x in Rn such that lim sup is not equal. And that's this lim sup, not equal to lim inf. That's this lim inf. So let's look at that set. That's the set of points where the partial derivative does not exist. Now, notice that look at this function, look at this quantity here, this one. Yeah, so this is, look at this quantity. It's the limit as h tends to 0, and let's call it t, maybe better. T tends to 0 of fx plus t en minus fx over t. That's what this is whenever it exists, at least. That's what it is. Now, notice that this, and as I said, this is d dt. Whenever it exists, it's exactly the same as d dt of fx plus t times en, evaluated at t equals to 0. So exactly the same thing. So what about that? Well, notice that that quantity there, fx plus t en, if you hold x fixed, then this quantity is a Lipschitz function of t, for t on the real line. So is a Lipschitz function of t. In the real line. And remember, part of your theory, I think you probably had a course or two in analysis, so you know that Lipschitz functions on the real line, one of the properties of them is that they're differentiable almost everywhere, functions of one variable. So hence, this does exist. D for every given x, without exception, there's no exceptional x's. For every given x, this quantity dnfx, ddt rather, of fx plus ten, that exists for almost every t. This for L1, almost every t in R. Notice we're talking, x is fixed here, so we're talking about just one variable. So we're talking about one-dimensional Lebesgue measure, right? So we have that property. Now, think about that. That means that this set E, this is the nice observation, the set E, well, first of all, I forgot to mention something here about this set E. I claim that E is a Borel set, which I should have mentioned up here. So claim E is a Borel set. That's not at all obvious by looking at it, but you see this. Let's look at this lim sup. Let's check that it's a Borel set. Let's look at lim sup as h tends to 0 of fx plus hen minus fx over h. Well, remember, by definition of lim sup, that's the limit as j tends to infinity of the sup of mod h bigger than 0 less than 1 over j. Sup from mod h less than 1 over j bigger than 0 of this quotient. Like so. Now, this is now these are continued for a fixed h. Now let's take h fixed for a minute. For a fixed h, this guy is a continuous function of x, trivially. In fact, it's a Lipschitz function of x. So it's a Lipschitz function for each fixed. So Lipschitz for every fixed h. So here we're taking the sup over a family of continuous functions. Now, I don't know if you've seen this fact before. It's just one line to check it, actually. But the sup of a family of continuous functions is always lower semi-continuous. You can easily check that, just one line. So this sup, it's the sup of a family of continuous functions, so it's lower semi-continuous. And hence Borel. Remember, upper and lower semi-continuous functions are Borel measurable. So this is a Borel measurable function. Borel measurable function of the variable x, of x. And then the limit of a sequence of Borel measurable functions, of course, is again a Borel measurable function. So that means that this is the set of points, this set E that we cooked up here, is the set of points where two Borel functions differ, where the difference is not equal to 0. Well, that's a Borel set then, by definition. So this is certainly a Borel set. Okay, so that's good. It's a Borel set. We need that in a minute because we're going to use Fubini's theorem. And you must remember, if you want to use Fubini's theorem, you've got to have measurability of the set that you're applying Fubini's theorem to. Fubini's theorem is, of course, false if you don't have measurability of the set. Okay, but we have that here. We have even that it's a Borel set, so it's certainly Lebesgue measurable set. Now, so let's go back to this argument. This is a Lipschitz function of t, hence for every x, without exception, this derivative exists for L1 almost every t in R. Now, you see, that means that the set of, that is, L1 of E intersect the set of x plus t E n such that t is in R. That set has Lebesgue one-dimensional measure 0. Sorry. So we're talking about one-dimensional Lebesgue measure, so that makes no sense. So I mean L1 of the set of t such that such that xt is in E. That's where that's the set of t such that xt is in this set E where this doesn't exist, right? Now that has L1 measure 0. So the L1 measure of this is 0. It's the same statement as this. So L1E is 0. But now Fubini says exactly, what does it say about the Ln measure of a measurable set E? It says that you can get the Ln measure of a measurable set E by slicing it in the nth direction and then integrating that over the remaining variables, right? So according to Fubini, this is the integral over Rn minus 1 of the measure of this set, the L1 measure of this set of t, such that, sorry, this is not correct notation. It's supposed to be x plus t E n. Sorry. That's the notation we're using here, x plus t E n. And let's use a slightly different notation here. Since we're talking about variables in Rn minus 1, let's rewrite this. Instead of writing it as x plus t E n, let's rewrite it as yt, where y is now the first n minus 1 variables and t is the last variable. So this set of t such that yt is in the set E, and then you integrate with respect to L minus 1 dimensional Hausdorff measure with respect to the variable y in Rn minus 1, right? That's what Fubini's theorem says. But then that's 0 because all of these terms are 0. That's what we said here. So this is 0. Okay, that's good. So that means that the partial derivative, the nth partial derivative, dn, the nth partial derivative of f at x exists for Ln almost every x. In Rn. So that's nice. And of course, there's nothing special about the nth partial derivative. That's just a notational matter. Equally well, you could prove that the first n minus 1 partial derivatives. In fact, we can prove that all the directional derivatives exist almost everywhere now. Because, let's do that here. So, take any v in Sn minus 1. And remember, of course, there exists an orthogonal transformation. Let's call it Q from Rn to Rn with Q En equals V. You can always take an orthogonal transformation that rotates En to the given vector V, right? They're both of length 1, so you can do that. And then you can define a new function h tilde of x simply by defining h tilde to be the composite function. H tilde equals h composite q. Oh, sorry, we're talking about f, aren't we? So f tilde equals f composite q. And that means that f tilde of x plus Ten is the same as f of qx plus qen, but qen is equal to v, so plus tv. So that means that the nth partial derivative of this new function f tilde at x is the same as the directional derivative by v of f at qx. And of course, orthogonal transformations don't change the Lebesgue measure, so we know that this exists almost everywhere in Rn, so that's the same as saying it exists. This guy exists. In fact, we could rewrite this. You can use the inverse, which is the adjoint of Q. So Q star x equals dfx, like that. Either way, same statement. So this is true for Ln almost every x in Rn. So all the directional derivatives exist almost everywhere. However, you must be extremely careful about that. The almost everywhere depends on which v you're talking about. So you get a different exceptional set of measure 0 for each choice of v. So you have to watch that. It's not just one fixed set of measure 0. Okay, so that's, in fact, we're going to respect that in the rest of the proof too by using a countable dense set of these v's. So let v1, v2, etc. be a countable dense set. Countable dense set of vectors in Sn minus 1. So that means in particular that for every epsilon bigger than 0 and for every epsilon bigger than 0 and for every v in Sn minus 1, there exists some j with the distance from v to vj less than epsilon. In particular, in fact, you can do that for every epsilon. It's a countable dense set. The closure gives all Sn minus 1. So you can get as close as you like to any given v. In particular, we can get within epsilon of a given v. So we're going to make use of that in the rest of the proof now. So let me just pause for a minute and remind you where we've got to so far. So far, we had to struggle a bit, but we eventually proved that all of the directional derivatives exist almost everywhere. That's good. So let's just write down what that means. In fact, here it is. Yeah. So let's do this. Okay, so here's our definition of the directional derivative. That now exists for almost every x, Ln almost every x in Rn. So thus, EVFX absolute, oh, let me write it this way. Fx plus tv, let's call it t instead of h, minus fx minus t times dv, the directional derivative, fx. So dv, so this dv fx exists for ln almost every x in Rn, and by definition that of directional derivative, that means this guy, t to the minus 1, tends to 0. So we'll make use of that. Now before we do that, before we come back, I want to come back to that in a minute, but there's one other tricky preliminary step to make now concerning these directional derivatives. Notice that, let's look at the difference quotient. So let's look at just this part. So fx plus tv minus fx over t. And let's multiply that by a function, let's call it zeta of x. Zeta is going to be a fixed C infinity function with compact support in Rn. So this means all the partial derivatives exist and are continuous. All the partial derivatives of all orders exist. All the mixed partials of all orders exist and are continuous on Rn. And this means compact support. That means that zeta is identically 0 outside some ball. And let's integrate that. And integrate with respect to Lebesgue measure. So x is the variable. We're integrating with respect to Lebesgue measure. And t is fixed for the moment, right? So t is fixed here. T not equal to 0 fixed. Now, notice I can make a change of variable here. I can make a new variable in this part of the integral, this times zeta. I'll leave this times zeta fixed, but I want to change this variable, this times zeta. So I'm going to make a new variable y equals x plus tv. Now notice that's just a translation because t is fixed, right? So this is just a translation of the x variable. So this becomes fy, and dx becomes dy, of course, because it's just a translation. Doesn't change the measure. And now we've got to be careful. Then this factor, zeta x, becomes, let's see, this is equivalent to saying that y is equal to, rather, x is equal to y minus tv, right? So we've got to remember to put y minus tv there. But when we've done all that, I want to change the dummy variable y back to x again, right? So I'm going to write everything in terms of a variable that I call x. So doing that, notice we get a minus sign because, well, in fact, what you get is this. Integral over Rn of fx. And this, as I said, becomes zeta x minus tv. Mustn't forget that. And then we still have this guy, minus fx times zeta x all over t. So that's what you get when you make that change of variables, dx. And notice that there's a common factor of fx here. So this can be written as minus the integral of fx times zeta x minus zeta of x minus tv all over t. ln x. That's sort of a finite integration by parts formula. It's very, you often use this trick in real analysis, in particular in partial differential equations. You often use this trick of making this change of variable. It's sort of a finite integration by parts formula. See, it looks very much like an integration by parts formula, except that instead of actual derivatives, you've just got difference quotients, right? The only thing you've got to keep in mind is this minus sign, which keep that in mind. Okay, now I'm just going to let t tend to 0 here. Now remember, all these difference quotients are bounded because f is Lipschitz. So therefore you can use the dominated convergence theorem. And as t tends to 0, we know that pointwise this tends to the nth partial tends to the directional derivative rather in the direction of v. So let t tend to 0 and use the dominated convergence theorem. Then that tells us that this becomes the directional derivative, dv, by definition. dv exists, so this is integral over Rn dv fx times zeta of x dln, or let's just call that dx. I mean, that's standard, isn't it? Instead of rewriting that clumsy thing, you simply write dx. It's the standard abbreviation for that. And this is the same as minus. Now this tends to just the directional derivative of the smooth function zeta. So it's minus the integral of fx times dv zeta x dx. So now zeta is just a smooth function, so you can just use ordinary calculus on that. That's just by the chain rule. So you just use the chain rule for smooth functions. And the chain rule says that dv zeta, by definition, that's just d dt of zeta x plus tv. And by the chain rule, that's just the sum from j equals 1 up to n of the jth component of j times the jth partial derivative of zeta at x. And if we want to evaluate it at t equals 0, then that's fine, which is what we want to do. So it's that. So that's just calculus, chain rule. So this side can be written as minus fx times the sum j equals 1 up to n vj times dj zeta. Okay, so that's our identity. Now, let me, in fact, it does not do flash. Let's minus the sum minus f of x times the sum j equals 1 up to n dj f zeta of x dx. Now we can use Fabini again, using writing the sum outside and using the Fabini by integrating first with respect to the jth variable. While we're at it, let's take the vj outside too. I guess I should have left it there in the first place. So vj times the integral of fx times that is over Rn. Now you can first integrate with respect to the jth variable by Fabini, but that's just a one variable calculus integration by parts formula. So we can put the derivative from here onto f. Remember, that's okay for a Lipschitz function of one variable. We know that. The integration by parts formula is well known for functions of one variable. So I can rewrite this as plus, because when we do the integration by parts, we always get another minus sign. And then it's the sum, j equals 1 up to n, vj times the integral over Rn of djf x zeta x dx. So another way to say that is we could put the sum back inside now. So this is, that is that dvfx zeta x dx, oh, sorry. No, zeta is a common factor. So it's dv of f, I'm going to take this over the other side. So dv f of x minus the sum, j equals 1 up to n, dj fx, all multiplied by zeta dx is equal to 0 for every zeta which is C infinity with compact support in Rn. Oops, this is integral over Rn. Now, of course, you know that there's no way that could be possibly true for every zeta. For instance, you can let zeta approximate the so-called Dirac delta function, and it picks out values of this function. So the only way that can possibly be true is for this function to be identically 0, right? So that's what you conclude. So that is dvf, the directional derivative, not only exists, but it's also given by the usual calculus formula, sum j equals 1 up to n of vj djf of x. And that's true for ln almost every x in Rn. So that's the that part of the proof is somehow. I probably could have just told you this was true, and you might have believed me. But it's not obvious because we only proved that the directional derivative existed. We didn't prove it had to be given by this usual calculus formula, right? So we had to check that. Okay, so that's one of the main steps of the proof. Now we're almost finished. So we've got this countable dense set of VJs where we have this difference quotient 0. Here they are here. And we've now got this additional formula that works for ln almost every x in Rn. So now let for every j, I'm going to consider these VJs again now, this countable dense set. So let Aj set of x in Rn such that dvj fx exists, and all the partial derivatives individually, such that they all exist, and they're given by this standard formula, dvj fx equals the sum. Now I better be careful, I'm using a dummy variable j here, so I've got to use a different dummy variable here, so let's call that I. Sum I equals 1 up to n vi, vij, that's the ith component of the vector vj, times di fx. So that's aj. Now we've proved that that's the complement of that has measure 0. That's what we proved. Is we proved directional derivatives and all these things hold almost everywhere. So that's true for every j. And now let A be the intersection of all these. And notice that that's still almost all of Rn, because if you take Rn minus that intersection, Rn minus A, that's Rn minus the intersection, which is the union of the separate complements, right? So they're by De Morgan's laws. So this is the union j equals 1 to infinity of Rn minus Aj. Union. And that's less than or equal to the sum over j of ln Rn minus Aj, and they're all 0. So that's still equal to 0. Now the claim is, and we'll check this after the break, the claim is that A is the set where the differentiability holds. I claim that F is classically differentiable for ln almost every x in A. In fact, for every x in A, without exception. And of course, that will be the end of the proof, because the complement of A does indeed have measure 0. So we'll check that at the after the break. So let's take a 10-minute break. j. This holds for every j if x is in A, because A was defined to be the intersection of all these sets. So we can freely use that identity for every j. Now let's observe that what this means. This by definition means, so let's just rewrite that. So that is for every x in A and for every j equals 1, 2, etc., we have this existing and is equal to that. So we have limit as t tends to 0 of t to the minus 1 times f x plus t vj minus fx minus the sum I equals 1 up to n vij d i's partial derivative di fx that has a limit 0. So we have that to work with. Now let's use the epsilon delta definition of that. So let epsilon be bigger than 0 given, and then this limit 0 means that this is less than, so it means there exists a delta. Now let's be careful. Delta is going to depend on x and a. In particular, let's remind ourselves carefully that it's at least going to depend on j. It's also going to depend on which x we're talking about as well, but it's in particular going to depend on j. So there exists a delta j bigger than 0 such that this is less than epsilon for mod t less than delta j bigger than 0. So that would be the epsilon delta way of saying that that limit is 0. So that's what we have to work with now, and I claim that it does imply differentiability. So let's check that. So let's look at the difference quotient. So take y not equal to x. X is in A. And let's look at the difference quotient. Fy minus fx minus y minus x dotted with grad fx absolute value. Let's look at that. Okay, well, let's just change the notation slightly first of all. So I'm just going to change the notation here. I'm going to let y minus x equals tv. Let's write it like that, where v is going to be the length of the vector. V is going to be the unit vector, so it's going to be y minus x over the length of y minus x, and t is going to be the length. Of course, you can always do that for any vector. So rewriting that, this becomes t to the minus 1 f x plus tv minus fx minus, and now y minus x is tv, so this is minus t times the sum j equals 1 up to, oh, look at that. I'm very sorry. I've left out the t here. Okay. Did I do that anywhere else? I have a feeling I might have. Anyway, that's the definition of differentiability. So we mustn't leave out the t. So j equals 1 up, j equals, let's call this I since it may fit in better with our later discussion. I equals 1 up to n of vi di fx. So we can write it like that. And then I want to use these VJs. So now for every v, there's one of these vj's less than epsilon. Of course, it'll change as you change v and t, but for fixed t and v, you can pick a j. So let's do that, right? So that's, we can rewrite this. So we can rewrite this as t to the minus 1, fx plus tvj minus fx minus t times sum I equals 1 up to n vij di f of x. But clearly that's an error. I've made an error. I've got to put in the difference terms to make this correct. So this is the correction terms are fx plus tv minus fx plus tvj. And then the other correction terms involve this. This would be the remaining correction terms of vij minus vi. So vi minus vij, actually. So t times vi minus vij times di fx. Like that. So that's what you get when you do the correction. So it's the same thing. I didn't do anything, right? These terms cancel out. That cancels with that, and that cancels with that. So I didn't do anything. Now let's use the triangle inequality. And notice that triangle inequality. So notice that this one is vi. This one is v minus vj dotted with the gradient. So I'm going to rewrite this one as v minus vj dotted with the gradient of f. So t times v minus vj dotted with the gradient of f at x. Okay, that's good. So we have that. Now we can use the Lipschitz. Now, first of all, this one is going to be less than epsilon as long as we take t less than delta j. So let's see. So yes. So notice we could have been a bit more clever here. This is a countable dense set. So actually I can pick just a finite collection of these v's. Since we've got a fixed epsilon, I can pick a finite collection of v's that has this property, that for every v in Sn minus 1 there exists a j with this. So let me say it that way, since it's exactly what we need here. So since this is a countable dense set, for every epsilon bigger than 0, we can find a finite set. For every epsilon bigger than 0, there exists v1 up to vn, some finite collection with such that this is true. For every v, there's one of these j's. For some j, there's a j just in this finite collection, 1 up to n. That's going to be important right now, actually, because we've only got finitely many deltas to worry about now. So as long as I take, so I can pick vj so that mod v minus vj is less than epsilon. That's what this says. And for some j equals 1 up to n. Okay, so then let's see what we can say about this. So, okay, this guy, according to this, should be less than epsilon as long as we take mod t less than delta j. So this first term is less than epsilon. And we've got to keep track of the conditions. This one is less than epsilon of mod t is less than delta j, bigger than 0. This guy, let's see, what about this guy? Well, this guy is less than or equal to L times the distance between v and vj times t, but the t's cancel, you see? So it's just less than L times v minus vj. Oh, look what I did here. I put in the absolute values, but I forgot to put in the 1 over t's. Likewise here. So that T cancels out. So that's the correct formula with the T's in place. And then this is less than, by the Lipschitzness, this is less than V minus Vj, but that's less than L times epsilon. Likewise, by Cauchy-Schwarz inequality, you remember the Cauchy-Schwarz inequality, right? That if you take two vectors A and B in Rn, then absolute value of the dot product is less than or equal to the separate product of the separate lengths. So we use that here. So this is less than epsilon again, and this is again less than L because it's a Lipschitz function with Lipschitz constant L. So we get, also from this term, we get an L times epsilon. So let's see, let's add up. How many epsilons did we get altogether? We got 2L plus 1 times epsilon. And trouble is this depends on J, and we don't want that. We don't want a dependence on J. So let's just take less than delta to be the minimum of these deltas. Notice we've only got a finite number of delta J's to worry about here. J equals 1 up to n. So take delta minimum delta 1 up to delta n. That's still a positive number. And then we get 2L plus epsilon. That's it. That's the differentiability. So that a little bit tricky proof, but it really is elegant, and that's C.B. Murray's proof of the Rademacher theorem. I think Rademacher's original proof was rather more complicated than that. Okay, so that's Rademacher. Now, there's a nice consequence immediately of Rademacher. It's called the C1 approximation theorem. So, corollary. So, theorem. This is the C1 approximation theorem. So suppose f is a Lipschitz function, Rn to Rn. Then there exists a C1 function on all of Rn, a C1 function g. Remember, this means all the partial derivatives exist and are continuous. So this is a function from Rn to Rn, to R. Everything is, oh, sorry, f is real valued. So we're talking about real valued function. So the claim is that there exists a C1 function g on Rn such that the Lebesgue measure of the set of x such that fx differs from g. In fact, you can even take the union of that in the set of points where the gradients differ, such that grad fx exists and grad fx is not equal to g, grad g. So it's actually the union of two sets. It's the set of points where f differs from g and the set of points where the gradient of fx differs from the gradient of g. The claim is that you can make that as small as you like. So for every epsilon bigger than 0. If you pre-assign a given epsilon bigger than 0, you can find a C1 function g such that the set of points where f differs from g together with the set of points where the gradient differs from the gradient of g less than epsilon. Oh, yes, sorry. Lipschitz. That would have been a very good theorem without that hypothesis. I'd like to prove that. Now that actually is pretty amazing, in my opinion. because it's not just saying that you can approximate f closely by a C1 function. That's trivial. You just use a smoothing process. You can always approximate any L1 function by a smooth function in just about any, well, an L1 function in the L1 norm you can approximate by smooth functions, and a continuous function you can approximate in the uniform norm by smooth functions. But this is saying much more than that. It's saying that even the set of points where they actually don't stick together is even small. So here's the picture. Here's your Lipschitz function. Remember, this is just a schematic picture. It could be really much worse than that, right? It could be a lot worse than that. Then you're saying that you can find a smooth function which somehow sticks to this with no error. It literally sticks to it with the same value, not just close, but actually the same value, except for a set of small measure. So it's a pretty amazing theorem. So I claim that it follows this. We're going to use Rademacher's theorem, and we also have to use the famous Whitney extension theorem. So I've got to tell you about that before I can give the proof. So the Whitney extension theorem. So Whitney extension theorem. Whitney was a mathematician who lived in the first half of the 20th century. Who proved he was an amazing mathematician. He did a lot of work on the structure of algebraic sets and things like that. Very fundamental work. And the Whitney extension theorem is really an important theorem. It says the following. Suppose that C is a closed subset of Rn. It's a closed subset. Closed subset. And suppose that you've got two functions, one a vector function with components nu1 up to un. So this would be a mapping into Rn then. So it's a mapping from C into Rn, into Rn, n components. And you've got another one, H, is a mapping from C into R. So H is real valued. So you've got a vector valued function and a scalar valued function, and you suppose they're both continuous. And the following rather strange looking condition holds, namely the limit. I'll explain this condition in a minute, and you'll see that it's actually very natural. The limit as y tends to x, y in C, of hy minus hx, yeah, that's right. Hy minus hx minus y minus x dotted with this vector function mu at x. That limit divided by the length y minus x, that is equal to 0 uniformly for x in each compact subset K contained in C. So I'll explain that condition in a minute. I'll explain why that's a very natural condition in a minute. For the moment, it must look a little bit odd. That's the hypothesis, anyway, of the Whitney theorem. You suppose that you've got two such functions, a vector function and a scalar function with this property. Right? Now, I'd better make clear what this uniformly for x, that means that is this limit that for every x in K, there exists, for every epsilon bigger than 0, and for every compact K, there exists a delta bigger than 0. such that this quotient hy minus hx minus y minus x dotted with nu at x over length y minus x is less than epsilon for every x in k. You see there, that's what the uniform. You see the the delta doesn't depend on x. It only depends on which compact set you're talking about. For each compact k, of course, contained in the set C, it's got to be contained in C, otherwise it makes no sense. So that's what the uniform thing means. And the conclusion of Whitney's theorem, these are the hypotheses. The conclusion is that there's a C1 function defined on all of Rn, function G from Rn to R, such that G restricted to C is equal to this H, and gradient of G restricted to C is equal to this vector function u. So it says that whenever you've got a pair of functions, vector function and a scalar function like this, then you can always find a C1 function which is defined on the whole of Rn and which matches H on the set C, and the gradient matches nu on the set C. Really lovely theorem, incredible theorem. I don't have time to prove it here, but if you look in the text, you'll see a reference to where you can find a proof of this. Now, I want to explain why this is natural. Because, you see, actually, the thing is, this condition here is not only, Whitney's theorem says that this is a sufficient condition to guarantee there's a C1 extension function, right? But actually it's also necessary. That explains the thing. Actually, if you already have, so note, if C is closed, if the hypotheses are as here, if hypotheses are as above, so same hypotheses on nu and h, and if you already have a C1 function, if G is C1 with G equals H, and gradient, this is G restricted to C, and gradient G restricted to C equals nu, then you'll notice that you can then look at the, let's look at this. Gy minus Gx minus y minus x dotted with the gradient of Gx, absolute value over y minus x. Limit of that is equal to 0, of course. But but we can actually do a bit better than that. We can say a bit more than that. Let's try to do that. So this can be rewritten, let's see, Gy minus Gx. That can be written as, I can use calculus to compute this. So this is actually can be rewritten as the integral from 0 to 1 of derivative with respect to the t variable of Gx plus t times y minus x dt minus this thing still, dotted with gradient of Gx over y minus x. That's correct, isn't it? Because when I integrate, I get, this is the integral of a derivative. So at the top limit of integration, I get t equals 1, so I get x plus y minus x, which is g at y. At the lower limit of integration, I get t equals 0, which is g at x. So that's the same thing, just written in a different way, right? And on the other hand, but we can use the chain rule to compute this. By the chain rule, this is equal to the gradient equals y minus x. Just take the chain rule. The derivative with respect to t of this gives us y minus x factor dotted with the gradient of g evaluated at this point. So in fact, this is actually equal to, there's a common factor of y minus x here. So this is y minus x dotted with the gradient of g at x plus t times y minus x minus the gradient of g at x, all divided by mod y minus x. And by Cauchy-Schwarz inequality, notice this is a unit vector now here, this ratio, right? Unit vector. So by Cauchy-Schwarz, this is less than or equal to length of gradient g at x plus t times y minus x, whoops, t times y minus x minus gradient of g at x. And you see, yeah, in fact, you see that then that's the point. Notice that this clearly tends uniformly to 0 because it's just the continuity of g. So this tends to 0 uniformly in x as y tends to x, for x in a compact subset of k. So this condition is just the natural one. Of course, what Whitney presumably did when he was trying to work out what the right extension theorem would be, he started off with a given g and just did this computation or something like it. I don't quite know. I wasn't there. But he did something like that. And he worked out that what you would actually need is this sort of, so you'd need to have a function to play the role of grad g, and you need to have another function to play the role of g on this closed set C. And the natural hypothesis is that this difference would then have to tend to 0 uniformly. So this is not only a sufficient condition for the existence of a g, it's also necessary. It's equivalent to the existence of a g. So this condition makes perfectly good sense. There's nothing odd about it. Yes? Say that again? Oh, yeah, I'm sorry, it didn't disappear. Yeah, I'm sorry. It's the integral from 0 to 1 dt. Yeah, it didn't disappear. Let's see. I should have, yeah, I cheated you a bit there. Let's see. This is less than or equal to absolute integral from 0 to 1 of, so we put the absolute values inside. Notice you can put this term inside the integral, you see, because the integral from 0 to 1 of this constant is equal to the same thing. So I can rewrite this as the integral from 0 to 1 absolute value less than or equal to the integral from 0 to 1 of the absolute value of the difference dt. So there's still an integral there, but it doesn't change this statement. Yeah, thanks. Thank you. So there's nothing odd about the Whitney theorem, the hypotheses rather of the Whitney theorem. It's a perfectly natural statement. It's exactly necessary and sufficient statement. And the point of Whitney's theorem is he's claiming it's sufficient to guarantee the existence of G.
But in general, the C, the closed set, high codimension, could be very thin.
It could be extremely thin, right? But right, so it doesn't really matter. You see, there's two ways of looking at that. If the set's fat, then we've already got a function on a big set. That's good. Whereas if the set's thin, okay, we've only got a function on a small set, but we've got so much flexibility on defining the function in the rest of the set, right? It's like that. And the proof is very non-trivial. It uses so-called a Whitney partition of unity is one of the great ideas of mathematics. A Whitney partition of unity. It's a really terrific...
the definition of the,
yeah.
the limit at the very beginning.
Yes.
Is really not quite full information of derivative. It's just partial derivative. Quite partial because x and y are sitting there.
Yes, but on the other hand, see, this is already saying something like differentiability as far as these guys are concerned, you see. This is not just the sort of thing that you would that would guarantee partial derivatives exist. This is the sort of thing that will guarantee differentiability in the proof, right?
I mean, that's really kind of full derivative.
But I think what I mean is that the set is small. Why is only true for
Yeah. No, that's right. If the set's small, then of course, for example, if the set's empty, no problem. Just take G to be a constant. And if it's a line, then you can easily give a trivial argument to prove there's a G, right? It's only when C is a really strange-looking set that it starts to get really interesting, right? Yeah. Okay, so that's the Whitney theorem. Unfortunately, as I said, I don't have time to prove that, but if you're interested, you should take a look at the proof. It's really a great piece of work. It's one of the great works of modern analysis, this theorem. Uses Whitney partition of unity, and many analysts have since used Whitney partitions of unity, me included, actually. Okay, so let's now give the proof of the C1. Let's give the proof now of this C1 approximation theorem. So, proof of the C1 approximation theorem. Okay, so let's start off by taking, so let's, okay. So the main idea of the proof is that we want to somehow reduce the result down to this, down to the Whitney theorem. So that means we've got to try to cook up functions, we've got to try to cook up a closed set, C, which at least includes everything except a set of measure epsilon. We've got to cook up a closed set C and also vector function and a scalar function which satisfy those hypotheses. And we would want, of course, the function, in this case, since we want to get this result for f, we would want to cook up our function h so that it was the same as f, right? So at least on the set C. So that's sort of the idea of the proof. So we're going to try to do that. So, we know that f is differentiable almost everywhere. That's what the Rademacher theorem says. So Rademacher implies that f is classically differentiable Ln almost everywhere. So therefore the limit as h tends to 0 of f absolute fx plus h, this is vector h tends to 0, minus fx minus h dotted with grad fx. Actually, I'm not sure whether I want to use that notation. Let me just check. Otherwise, I'll get in a big mess. One thing I found out is that if I change notation at the beginning of a proof, I'll inevitably get stuck. Yeah, so let me stick to this notation. So let me stick to the same notation that we were using before. So limit as y tends to x. Fy minus fx minus y minus x dotted with grad fx is equal to 0. And so that's given. And then that means that you've got, let's define a function eta of sub k of x. So define eta sub k of x equals sup mod y minus x bigger than 0 less than 1 over k. For each integer k equals 1, 2, etc. We're going to do this. And take this sup here. So over that. So take sup. And that means that e to k tends to 0. This statement says e to k x tends to 0 ln almost every x. Now, we'd like to use Egorow's theorem. Remember, Egorow's theorem says that if you're willing to throw away a set of small measure, then you can get uniform convergence instead of convergence. However, we mustn't cheat. That was for sets of finite measure, and here we're working on all of Rn. So we should use Egorow's theorem on, say, an annular region. You can always decompose. You can take the ball of radius j minus the ball of radius j minus 1 at 0. And notice you can decompose all of Rn that way. Union j equals 1 to infinity. Well, actually, I suppose, let's see, when j is 1, that's the ball of radius, closed ball of radius 0. That's just a single point, isn't it? So actually, all except the origin can be written that way anyway. So Rn minus 0 can be written like that, where bj means the closed ball. Notice I always use b to mean the closed ball. If you want to use the open ball, you should use a different notation. You should help out the graders in your assignment work too. When you're using an open ball, you should use a different notation. This is a good one. This is the Breve symbol. There's a tech symbol for that, actually, if you haven't used it before. Okay, so so we can use that. So we can use Egorov on each of these annular regions. So Egorov, it's 1g. Egorov on bj minus 1 implies that there exists a measurable set Ej contained in bj minus 1 with the measure ln of ln of bj minus 1 minus Ej less than epsilon. Or actually, I could even make it less than epsilon over 2 to the j for the usual reason, because we're going to add things up after, such that, and e to k x tends to 0, e to k x tends to 0 uniformly. As k tends to infinity. On Ej. So it's uniform convergence. Now that's good, but we want to get closed sets and we want to get continuous functions in order to, we're trying to cook up continuous functions here. Look at that. Oh yeah, no, I did say it, that's good. I thought I'd forgotten to say continuous. It's part of the Whitney, so we're trying to cook up continuous functions. F is continuous because it's Lipschitz, but the gradient of f is not continuous, so we better worry about that. So, so that means we should use Lusen's theorem. Remember, Lusen's theorem says that you can throw away a set of small measure and be left with a continuous function. The restriction to what's left will be a continuous function. So by Lusen's theorem, which we proved last time, there exists Cj contained in a closed set, Cj, contained in Ej, with, again, with measure, choose up as much of the set as you want, so we can arrange that Ln of Ej minus Cj, again, less than epsilon over 2 to the j, no problem, and a gradient of f with respect, a gradient of f restricted to Cj continuous. Okay, now it looks like we're just about got what we want. See, we've got these, so let's do this. So now we've just almost got our set C, except that the trouble is we've only got a set Cj contained in this annular region. We want a C in all of Rn, but that's good. We can just take the union. So C equals the union. J equals 1 to infinity, Cj. Now, before you protest that the union of closed sets is not necessarily closed, think about it. These are unions of sets over separate annuli, so there's only finitely many of these annuli. They're disjoint sets, and only finitely many of them intersect any given ball, right? So this is still a closed set. It's closed. And so normally that wouldn't work because you usually can't take the countable union of closed sets, but these are well separated. So you can do that. That's closed. It's closed, and also Ln of Rn minus C, well, that's the union of the Cj, so remember that's less than or equal to, well, that's less than or equal to the sum over all these annular regions. So this is less than or equal to the sum, j equals 1 to infinity, of Ln Bj minus Bj minus 1 minus Cj. In fact, it's equal to that sum because they're disjoint sets. And that's less than the sum of epsilon over 2 to the j. So less than epsilon times the sum, j equals 1 to infinity, 1 over 2 to the j, which is equal to epsilon. So that's great. So, oh yeah, I actually probably made a mistake there, didn't I? Because here we had Ej eats up all but epsilon, and Cj eats up all but epsilon of Ej, so actually this is 2 times that. But that's okay, 2 epsilon is fine. We could have started off with epsilon over 2 instead of epsilon, so that's fine. So that's going to be our set C. That's our closed set C. And notice that grad f restricted to, so we're going to take nu to be equal to grad f restricted to C. And we're going to take h to be equal to f restricted to C. They're 2 continuous functions, and furthermore, by definition, they have this property. So, and notice that's uniform. That was the point of using the Egorov theorem. So actually, we're done. That's the hypotheses of Egorov hold. The uniformity is what Egorov was all about. Uniformly. So that's a really nice theorem, but it's as I said, it does depend on the Whitney theorem. I'm sorry I didn't have time to do that, but you should take a look at that. It's a really nice theorem. Okay, so we're making some progress. So that's the C1 theorem. We're going to C1 theorem will be very important for us when we talk about rectifiable sets a bit later. The C1 approximation theorem will be very important. Okay, so that's that. We've got about 5 minutes, so let me just introduce the next topic. Which is going to be Lipschitz images of sets, and so note that if you start off with if A is any subset of Rn, and you take F to be a mapping from A to Rn. Oh, in fact, this is a bit more general. Let's not be so specific. This is completely general. If X and Y are metric spaces, and if F is a Lipschitz mapping from X to Y, it's Lipschitz, then for every set A contained in X, so L, and if F from A to Y is Lipschitz, sorry, yeah, that's not right, and metric spaces, and if A is contained in X, and if F A to Y, so F is not defined on the whole, and it's just F is just defined on the subset A, Lipschitz, then the Hausdorff measure, n-dimensional Hausdorff measure of the image set FA is less than or equal to, it's less than or equal to the Lipschitz constant of F to the nth power times the Hausdorff measure of A. And A doesn't have to be measurable here, it doesn't matter. Okay, well that's really true just by definition. Let's check it out. It just uses the definition of Hausdorff measure directly. So let me take 1 minute to prove that. So proof. We're going to prove much more interesting results about Lipschitz images next time, but this is an important first step. And let's give the proof. So we want to talk about the Hausdorff measure of FA. Well, let's start off with this one. So for each I, if you look at the definition of Hausdorff measure of A, now you remember how that goes? You first of all define the size delta approximation by taking coverings, countable coverings of the set with sets of diameter less than delta. So I'm going to take sets of diameter less than 1 over I. So there exists Cj1, choose any cover actually, choose any Ci1, Ci2, etc. You can, with A contained in the union, Cij, and with A contained in the union, right. I think that's all we need for the moment. Then Hn, so then Hn, then Fa is contained in the union of the images, right? So union J equals 1 to infinity of F Cij intersect A. Oh, and I forgot to say diameter Cij less than 1 over I for every J. So I'm going to use the 1 over I approximation. So that's that. And And then what about the diameter of this guy, though? This has got diameter less than or equal to 1 over I. F is a Lipschitz function with Lipschitz constant, say L. Then remember, Lipschitz constant means the distance stretches by at most a factor of L. So that means these guys have diameter, those sets have diameter less than or equal to lip F times 1 over I. In fact, I could do this with this sort of dumb. I didn't need to do the I thing, I don't think. Let me just take delta positive. I think that's better. And A contained in the union of CJs. And diameter of CJ less than delta. Let's just do that. So there's only one index here, CJ, and the diameter of these images is less than lip F times delta. And that's less than 1 plus lip F times delta, of course, strictly less than 1 plus lip F. So that means that the size delta, the size 1 plus lip F times delta approximation to the measure. So we take 1 plus lip F times delta approximation to the measure of the image set is less than or equal to the sum J equals 1 to infinity of these guys. So it's sum diameter F CJ intersect A over 2 to the n, and we've got to remember to put in the normalizing factor omega n. So that's just the definition of the approximating Hausdorff measure. But then, as I said, just use this here. So this is less than or equal to lip F to the nth power. So lip F to the nth, so omega n is still there. So it's lip F to the nth power, omega n times the sum J equals 1 to infinity of just the diameters of what's left. Diameter CJ intersect A, or diameter CJ intersect A, or diameter certainly less than diameter of CJ, over 2 to the nth. There we are, so we have that. For any collection of CJs that you like to name which contain A with diameter less than CJ. Now just take the inf. Take the inf over all such collections. Take the inf over all such collections, and then this means that, so what does that actually give us? Then it gives us that Hn 1 plus lip F times delta, size 1 plus lip F times delta size approximation of the image is less than or equal to lip F to the nth power times, and the inf of this is exactly the size delta approximation of the measure of A, Hausdorff measure of A. So we get that. And now just let delta tend to 0. And we get this. So that's good. So that one's easy. So that's the first step, but we'll prove some more interesting things next time about that. Okay. Yep. Wash my hands.